So this semester, we're basing our research ideas on self-assembled monolayers. So this week and this module 2, we're making and characterizing self-assembled monolayers. The first thing that we need to do before we make the self-assembled monolayers is to clean the glass slides. We're going to be using glass as our substrate for our model substrate. And in order to clean them, we're going to use a concentrated sodium hydroxide solution. The purpose of this is to remove any dust or dirt from the surface, remove any organics, oils, greases from the manufacturing process or from fingerprints from people holding the glass slides. And it's also going to prepare the glass surface through hydroxylation so that we have a nice consistent surface across the entire surface. Now the molecules we'll be using for our model molecules for these molecular thin films, right, are aminosilanes. So to break this word up, aminosilanes, we have amino groups, which are nitrogen, NH2 groups, and we have silanes, so that's the silicon part. Now if you recall this picture from our discussion about SAMs in Module 1, we've got the head group. Remember, the head group is what attaches to the substrate. And we've got the functional group, and that's what's up, right? That's the top, now the surface on top of the substrate. So the head group in this case is the silane. If these are our two molecules that we could possibly be using, this silicon, right, and down is the head group. What's really going to covalently bond to the surface is this silicon atom. In the process of covalently bonding, this oxygen and ethyl group are going to leave the molecule and become ethanol, or methanol in this case. And then the functional group, the amine group, the NH2 group, that's on the other end of the molecule that we have here. Once these two, either one of these molecules, once they're attached to the surface, will have the same chain length with the silicon, and then 1, 2, 3 carbons, and then a nitrogen. When we form the SAM film, what we're doing is, this is not quite the same molecule, but it's very similar. We have that aminosilane. The silicon is what's going to bind to the oxygen that's on the surface, and this chain here, the oxygen and ethyl group, or methyl group, is going to leave and form that methanol, aqueous methanol. Now, all three, the silicon here could bind in multiple places here on the glass, or it could bind to other silicons through oxygen. But we're going to get a nice, hopefully ordered system where the silicon is all attached, covalently bonded to the glass, and the amino groups are pointing up. We'll get intermolecular forces, those London dispersion forces in between the chains that'll hold them together in a nice structured monolayer. And we'll get, referring back to our previous discussion, we'll get those head groups attached to the slide and the functional groups pointing up in a nice assembled monolayer. In order to do this, our general procedure is going to be to take those clean glass slides, soak them in 1 millimolar of a SAM solution for about 30 minutes. Once 30 minutes is up, you're going to rinse those slides with deionized water and gently blow them dry with the air that comes out of the lab bench. We're going to then measure contact angle of a clean slide and measure the contact angle of a self-assembled monolayer slide. And hopefully we'll see a difference between the clean slide with that hydroxylated surface and the SAM slide with the amine surface, now with that functional part up. In order to measure contact angle, you're going to be using that ImageJ software. Hopefully you get that before you come to lab. You should install that, follow all the instructions that are posted. And you're going to be taking pictures of drops of water that are on the surface, right? Here's the glass slide. And you're going to be taking a picture of a drop of water, and you're going to be measuring this as the contact angle right here. It's the angle between the tangent and the surface itself. So just to give you a little picture of what that looks like in a cartoon, here's the surface of the glass, right? We've got a drop of water. and we're looking at the angle between the surface and the tangent of the drop coming up, right, off the surface. If it's a hydrophobic surface, then that water will bead up and we'll get a pretty large angle there. If it's a hydrophilic surface, then that water will spread out on the surface and we'll get a very low contact angle. So here's just some characteristics of the surface, whether you have a hydrophobic surface or a hydrophilic surface. So your contact angle will be high with a hydrophobic surface or low with a hydrophilic surface. Adhesiveness of the water to the surface will be poor if you have hydrophobic, or good with hydrophilic. And then there's wettability, which is exactly what it sounds like. Solid surface free energy, that's something that we will probably talk about later this semester when we get into thermodynamics of sand formation. Now, how actually are you going to do this? You are going to build your own drop instrument, and you're going to use your phone, and you're going to set up maybe on a box some way to take a picture of the profile of that drop. You're going to try to make a consistent drop size on that surface, and then you're going to take a picture. You can import that picture into that ImageJ program, and you can measure contact angle using the drop snake.